Hello, can you guys hear me? Hello, am I audible? Can you guys hear me? Everyone? Okay, so before starting, let me introduce myself. My name is Santanu So, and I'm a PhD student, I'm a fourth year PhD student in the Department of Mathematics, IIT Madras, and I'll be doing TA for this course, for this introductory course in real analysis. So each week on Sunday, uh, I'll be taking 2 hour classes to solve some problems so that you guys can solve the assignment problems given in the main course. And in case if you have any doubts on the corresponding week, then you can always ask me questions here so that I can clear all of your doubts. Okay. So in the week one, uh, mainly three chapters has been covered. First is the countability and uncountability, that means countable sets, uncountable sets, and then the next chapter was matrix space, right? So first we're gonna recall some of the definitions that is required to solve some questions, and then we're gonna do some problem solving session. So what is a countable set? So first let us write the title. So countable sets. And a set is called countable if there is an one-to-one onto corresponding between the set and the set of natural number, because set of natural number is the like first countable infinite set, you can say, because that we can count easily, right, by 1 2 3 and so on. So a set is subset of R, let's say, is called countably infinite if there exists a bijection f from S to the natural number set. Okay, so this is the very fast definition of countable sets. So if you could found if you could find an bijection between the set and the set of natural number, then you can easily say that the set is countable. Now for example, you can take S to be the set of natural numbers, and then you can show that set of natural number is countable by taking the identity map, right? This is the much easier. And so this is the main definition of countable sets, and you actually don't need to prove bijection all the time, because it is not easy to show bijection, or it is not easy to find bijection given any sets with the set of natural numbers. So what you're going to do is you're going to go to the next definition of countable set. So there are also some other definition of countable set. So it says that if so let me give another definitions. So this is definition 1. Okay, so another is definition 2. So let S subset of R and it is called countable if there exists an injective map G from S to N such that if there is an injective map G from S to N. This definition is enough to prove that S is countable. So you don't need to find an surjective map. So if you can just find an injective map from S to N, this will imply that S is countable. Now why does this happens? So if there is an bijection, there is an injection between S and N, then you can show that this cardinality of S is less equals to cardinality of N. Okay. Now since we know that N is countable and cardinality of S can be at most the cardinality of N, so this will imply that S is countable. Okay. So this is another definition. And there is another definition in terms of surjection also you can prove. And this is definition 3. So a subset of R is called countable if there exists an onto map G from N to S. Okay. So now if there is an onto map G from N to S, then what gonna happen is the cardinality of S cannot be more than cardinality of N. Even there is an one-to-one correspondence between cardinality and this onto map. So here in the same scenario, you can show that cardinality of S is always less equals to cardinality of N. So if either you can found if you can find an injective map G from S to N, then also S will be countable. Or if you can find an surjective map or an onto map from N to S, then G will be S will be also countable. Okay, so you don't need to necessarily find an bijective map. So this is the definitions of, these are like three main definitions of countable sets. And a set is called uncountable if it is not countable, right? So a set is called uncountable if it is not countable, right? Okay. So now I just want to ask some questions to all of you. So this is an interactive session. This is not like just something I'll be doing and you guys will be listening. If you want to say something, you can always turn on your MIC and then you can speak. So I'm going to ask the question that, can you give me an example other than the set of natural number which is an uncountable set? Anyone?
Set of rational numbers.
Set of rational numbers. Why is it so? Do you know?
I did do that, but I don't remember right now.
Anyone know the proof why Q is countable? Okay, so before going to Q, what about the set of integers? I think someone wrote in the chat, right, that Z is countable, isn't it? Yeah. So who has written that? Bharat or something. So yeah, so do you know why Z is countable? So let me ask the first question, right? Why Z is countable? Anyone? Okay, so Z is countable because you can see Z as a union of set of natural numbers, set of negative set of natural numbers, and zero, right? Because uh, Z can be written like this. This is the set of natural number, union set of the negative set of natural number, union zero. Okay, so there are a lot of ways to prove Z is countable. One of the ways is this, that Z can be written as a union of three sets, and we already have proved that set of natural number is countable, right? Because of the identity map, correct? Similarly, you can show the negative of the identity map, and then you can show that minus n is also countable because it is just multiplication with a uh, number like -1. So since we know that countable union of countable sets are countable, so from here we can say that union of three countable set is also countable, right? So the first result or the facts we know is that countable, so not only countable, so let us go to finite first. Finite union of countable set is countable, right? So since there are only three sets which is countable, so that means Z is countable. So not only that, you can define a surjection from Z to the set of natural number. Not only that, even you can find a bijection from the set of integer to the set of natural number. Okay, so I'm gonna write the bijection just here. You guys can try to prove it. So the bijection looks like this. So you define from Z to n. Okay, so you define like this: f of n equals to 2n when n is greater or equals to 0, and minus 2n minus 1 when n is less than 0. Okay, now by this you can easily prove that this map is an bijection. Okay, so since it's a bijection map, that means by the first definition Z is countable, correct? So now, do you know what are the other sets than Z which is countable? So someone said Q is countable. So can anyone tell me quickly why Q is countable? Anyone, please? Yeah. Anyone know why Q is countable? Okay. So because Q can be seen as a as a product of two countable sets, right? So you see that if you write Q, so Q can be written as a ratio of the set of integers, right? Just except 0. So from numerator, if you just from denominator, if you just remove 0, then you can write Q as a ratio of the integers, correct? That is how rational numbers are created. So actually Q can be written like this, where P is in the integers and Q is in the set of natural numbers. And of course it is written in the reduced form. So reduced form means GCD of P comma Q is 1, correct? So this is how the set of rational number is written. Because if you write 1 by 2 and 2 by 4, both are same numbers, right? Both are same rational numbers. But 1 by 2 is written in its lowest form. That means the GCD of 1 comma 2 is 1, but GCD of 2 comma 4 is not 1, right? So that is how rational numbers are represented. So now can anyone take a guess how to prove from here that Q is countable? Can you see some connections here? Because I have already defined the components of the rational numbers, that is Z and N, right? Anyone? Okay. So what you can do is you can define a map uh, F from Q to Z cross N such that this F of P by Q equals to P comma Q, and you will be easily able to prove that this function is a bijection. Okay. Is it clear, everyone? Do you have any doubt? Anyone? Okay. So Bharat is writing okay. And what about others? Why is it a bijection? Anyone? Someone has written Q is countable if f equals to n by 2 when n is even. I think you are trying to find a bijection between the set of natural numbers and integer, right? Not Q. This way Q doesn't work. Okay, so this is an exercise to prove that this is a bijection, and the right side is actually an countable set, right? Because product, like finite product of countable sets are countable, right? So there is another fact that finite product of countable sets is countable. So by this logic, Z and N both are countable, right? So Z cross N is also countable, and since Q from Z to N is a surjection, so the cardinality of both the set will be equivalent, right? So that means the cardinality of Q will be same as the cardinality of Z cross N. So this will imply that Q is also countable. What about R, the set of real numbers? Is R countable? Is the set of real numbers countable? Hello, anyone? Is the set of real numbers countable? No, why? Why is it not countable? See, this is a 2-hour class. It will gonna be wrong. It will be a long class, so you can interact with me if you have any doubts. So first we're gonna clear all the doubts. We're gonna go through the basics, uh, like the basics of the first few lectures, and then we're gonna start doing questions. So someone has written that open 01 is uncountable. Yeah, that is true, but can you like tell me more elaborately what do you mean by open 01 is uncountable? Like how do you connect it with R? I can understand what you're trying to say, but yeah. Can you explain more? Yeah, so actually he's correct. There is no bijective map from 0 comma 1 to z. How do you know there is no bijective map? How do you know there is no bijective map? I mean, you have to prove it. In mathematics, if you say something, it doesn't mean you know it until you prove it, right? Okay, so open 0 1 is actually uncountable because of the Cantor diagonalization. I think you guys might have seen probably in the lecture videos, right? So fact this is gonna be fact 4. So open 0 1 is the set open 0 1 is uncountable. Okay, so I think you might have seen the proof, and if you not, then actually what you're gonna do is you're gonna uh, write all the decimal representation of the elements of open 0 1. Now since if it is countable, then you can write it like x1 x2 x3 so on like this. Then you're gonna write it like a matrix, and then you're gonna consider the diagonal elements. Now if the diagonal elements is something like say 2, then you're gonna take 3, and if it's like something like 3, then you're gonna take 2. So then this element will not belong to the enumeration. So this is actually called the standard Cantor diagonalization, and then you can easily prove that closed interval 0 1 or open interval 0 1 is not countable. Now how can someone prove that R is not countable, right? So there is another fact. So it says that let x and y be two any sets, any two sets, then x and y have same cardinality if there exists bijection if from x to y. So if there is a bijection from x to y, from a set x to a set y, then if x is countable, y has to be countable. Similarly, if x is uncountable, y has to be uncountable. Okay, is it clear? Is this fact 5 clear? So if there is a bijection between two sets, both will have same cardinality. Okay, so here cardinality refers to same category of sets. Like if x is countable, y has to be countable. If x is uncountable, y has to be uncountable. So there cannot be like there will not be a bijection between a countable set and an uncountable set. Okay, so now if we can somehow prove that there is a bijection between open 0 1 and the set of real numbers, then we can prove that R is uncountable, right? Because already we have just shown that open 0 1 is uncountable. So now can someone give me a bijection from open 0 1 to R? Do anyone know? So do anyone know any bijection from open 0 1 to R, a set of real numbers? Okay, so what I'm going to do is I'm going to find two bijection instead of one. So how we going to do? First we're going to find a bijection from 0 1 to minus pi by 2 comma pi by 2, and then to R. So let's say this is f1 and this is f2. So now the task is much easier, right? Because we have to just find an bijection f1 and another bijection f2, then we can do the composition. So then we're gonna get a composition like f2 composition of f1, and that will be a bijection from close open 01 to r. So now we have to just find out what is f1 and f2. So do anyone know, or can you just help me out here to find out an bijection f1 and f2? Anyone? So if you guys know something, you can interact with me. Otherwise, the class will feel boring, right? This is an interactive session. Sine function is, I think sine function doesn't work, right? And it is not bijective, first of all, because there can be a lot of values that can take like there can be a lot of points that can take same values. So sine function is never bijective. It's not even injective. That's why it's not bijective, right? So the first function you can define is this one. Okay, so you see that if you just take x equals to 0, or if you just take x approach to 0, then f1 of 0 is minus pi by 2. And if you take x approaches to 1, like x tends to 1 positive, then you're gonna get pi by 2. And this is clearly a bijection, right? Because this is just a proper scaling of the identity map. So first you take x minus half and then you multiply by pi. So this is a bijection. So do you guys know any bijection from minus pi by 2 comma pi by 2 to r? So we have already found out our f1. We need another f2, that is a bijection from minus pi by 2 comma pi by 2 to r. So do you know, do anyone know this map? This is a very common map. We have seen in our class 12th class. I mean, when we started studying like sine, cosine, tan, cot, that time we have seen. So now can you guys give a try? So you can do with me. That will be much easier to understand and to learn, especially this part of the mathematics. So if you solve with me, then only you'll be able to do it. Okay. So yeah, anyone know? Yeah, any idea how to prove? Because we have given all the information you required to prove this, or to solve this question, especially that the set of natural numbers, set of rational numbers, set of integers are countable, set of real numbers are uncountable, and obviously set of irrational number is also uncountable, because the set of real numbers is just set of rational number union set of irrational numbers, right? So since r is uncountable, q is countable, q complement has to be, I mean, the set of irrational number has to be uncountable. So there is no doubt that set of irrational number is also uncountable. But can you now solve this question? Anyone, any idea? So there are 20 people I can see, like, yeah. Any idea on how to solve this question? Anyone? Someone has written something on the chat. No. Yeah. Any idea? So one approach is that Cross products of two countable sets. Okay, what do you mean by? Okay, I mean, like, how do you prove? Like, what is to do with S here? So cross product of which two countable set? Are you like referring here from to like Q cross Q, or yeah? If you want, you can speak also. You can just turn on your MIC and then you can speak to me. So the idea is you have to find out an bijection from S to an countable set, or in other words, you can try to find an injective map from S to an countable set. So I'm gonna do is I'm gonna find out an bijective map between a countable set and that set S. So if you can do that, then by the above fact we just showed that if there is a bijection between two sets, then the cardinality of these two sets must be equivalent. That means if that set is countable, then S must be countable, because we're gonna prove an bijection between S and then the countable sets, right? So what you're gonna do is we're gonna define this map F from Q cross Q to S by F of P comma Q is P plus square root of 11Q. Okay. So is this understandable why I have defined this map? So F was a map from Q cross Q to S. So S is already this set of elements of the form P plus Q square root of 11. So now, can anyone tell me if this map is bijective? So let us go one by one. So can you now prove it that this map is injective? Anyone? So first we're gonna prove the injectivity, and then we're gonna prove the surjectivity. Any idea? Anyone? In the chat? Okay, if you don't want to speak, you can also write down in the chat, so then I can read and just try to understand like what's your thought process. So how to show that a map is injective? Anyone? Like what is the thing we have to do to show that a given map is injective? Anyone? Okay, so to show this map is injective, we have to prove that if f of p1 comma q1 equals to f of p2 comma q2, and this will imply p1 comma q1 equals to p2 comma q2, right? Is it clear? Mm. Okay, so now from the first equation, so this will imply p plus p1 plus square root of 11q1 equals to P2 plus square root of 11 Q2. Correct? So this will imply that square root of 11 is P2 minus P1 divided by Q1 minus Q2. Okay. Is it possible, anyone? Is it possible to write like this for distinct P1, Q1 and P2, Q2? Sorry, tell me. Yeah, tell me. If someone said anything, right? No, right? The answer should be no, right? Why is it a no? Okay, someone has written something. Okay, is it possible? Why you are saying is it possible? Square root of 11 is an irrational number, right? P1, P2, Q1, Q2 are all rational numbers. So that means you are saying that an irrational number can be written as a ratio of two rational numbers. Is it possible? No, right? That is the definition of irrational number, that an irrational number should not be written or cannot be written as a product of two or as a ratio of two rational number, right? So this is not possible. So that means P1, Q1, P2, Q2 cannot be distinct numbers. So P1 has to be equal to P2, Q1 has to be equals to Q2. Correct? So that means every distinct element is mapping to a unique element, unique distinct element. So this is implying a contradiction. So this is a contradiction. Correct? Hence F is injective. Correct? What about surjective? How to prove surjectivity? Anyone? So if you can prove surjectivity, then only we can say that the map is bijective. Now if the map is bijective, then we can say that S has the same cardinality as Q cross Q. Yeah, Bharat has written it correctly. So it is easy to see that this image of Q cross Q is whole of S. This is because you choose any element, say let's say x plus y square root of 11 from S, then you have to show that this has a pre-image. So since you have chosen any element from S, let's say x plus y square root of 11, then you take the image, the pre-image as x comma y. So that means you got a pre-image of that given element from S. So the pre-image of x plus y square root of 11 will be x comma y. So this is implying that the whole image of the set Q cross Q under F is whole of S. So this is implying F is onto. Onto or surjective, both are same thing. Okay. Is it clear? So F is bijective and this cardinality of Q cross Q is same as cardinality of S. Now we know that product of two countable set is countable, or in other words, product of finite number of countable sets are countable. This will imply that Q cross Q is countable, and hence S is countable. Is it clear for everyone? Is it clear, everyone? Hello, can someone say anything? Any reply, any comments, any doubts so far? Whatever we have taught now, countable, uncountable sets, the first questions. Any doubt? Okay, so I assume you guys have understood everything. So this is gonna be question number 2. Uh, the set of all straight lines passing through two fixed point is so the first option is not countable, second option is finite, third option is none of this. Okay, so any idea? Anyone? The set of all straight lines passing through two fixed point is a countable set, an uncountable set, or what? Is it like singleton or is it a finite set? Uh, so someone has asked to repeat the onto case. So to prove that this map is onto, you have to show that every element on S has a pre-image on the set Q cross Q. Okay, so you take an arbitrary element, let's say x plus y square root of 11 from S. Okay, I don't know what is x and y, so let's say this is an arbitrary element. Then the pre-image is just x comma y, right? Because f of x comma y is x plus y square root of 11. So given any element in S which is of the form x plus y square root of 11, f of x comma y is x plus y square root of 11. So this means that every element has a pre-image. So the range of f is same as the set S. So that's why f is onto. Is it clear? Okay, I hope so. So now come on to the next question. What do you guys think? The set of all straight lines passing through two fixed point. So let's see this is a graph of two dimensional, right? This is the R2 plane. So let's say this is a fixed point and this is a fixed point. So let's say this is P1 Q1 and this is P2 Q2. So now can you tell me how many straight lines you can pass through these 2 points? Anyone? Between two fixed points in the R2 plane, how many straight lines can you pass through? How many straight lines can you draw between given two fixed point in R2? It's, it should be one, right? It's very simple. There should not be more than one, right? There is only one fixed point, right? We also know the equation of the straight line, right? So this straight line can be represented. So let's say this is P, this is Q. Then the straight line L can be represented like this: P plus T times Q minus P. Also, we know the equation of the straight line, right? There is a formula for that. You guys know y minus y1 equals to, like, y minus q1 equals to q2 minus q1 divided by p2 minus p1 into x minus p1, right? This is a unique equation of a line, right, given to fixed point. So that means there should be only one straight line, correct? So since there is only one straight line, it should be finite. So this should be the correct answer, correct? For the last question, it was only countable. Yeah. So there is only one straight line that can pass through given two fixed points in the R2 plane. Okay. Is it clear so far, everyone?
Yes, sir.
Okay. So then I'll go to the next question. Question number 3. The set of all sequences whose entries are each either 2 or 3 is countable. Next option is uncountable. Next option is finite. Another option is none of this. NOTA, none of the following above, right? So yeah, any idea? Anyone? Yeah, anyone? So this is an like prime example of an application of Cantor diagonalization. So the same way you have to prove it, the way you have done when to prove that open01 is uncountable. Okay, but there are also other ways. to prove this is an uncountable set, but the standard one is the Cantor diagonalization. Okay, so what is the set? First of all, it is the set of all sequences such that each entry has either two choices, either 2 or 3, right? There are no other choices. So that means you can write this set like this. So this is collection of all sequence such that xn is either 2 or 3 for all n, right? So that means you choose any sequence where the elements should be either 2 or 3. So you may either choose 2 2 2 all, or 3 3 3 all, or 2 3 2 3, or whatever you choose. For example, mm, this sequence, let's say 2 3 2 2 3 2 and so on, this belongs to S. So the elements of the sequence must not be other than 2 and 3. Okay, so we have to prove that uh, this set is uncountable. So what is the guess? Should it be countable, or should it be always uncountable? Because I am saying doesn't necessarily mean you have to believe it until you understand yourself. Okay, okay. So let's say there's in mathematics the standard things when you try to prove something is called method of contradiction. So if you want to prove something and you cannot do it, then you can start with the negation. So let's say it is a countable set. Okay, so if S is countable, then we can number all the elements in the set S, right? That means we can number all the sequences in the set S. Okay, so let's say S has an enumeration. So let S is countable. Suppose that. Okay, then there exists an enumeration of S. Okay, so it means that every elements of S has a 1 1 on to correspondence with the set of natural number. So that means you can count uh, uh, like through an injective map, uh, like you can count the elements of S through an injective map to N. Okay, so this is what it means. So now what you're going to do, if there is an enumeration, we're going to try to write every elements of the set S, and then we're going to construct a sequence, and then we will show that the sequence does not belongs to S. And if you can do that, then we can guarantee say that S is not countable. Because if S was countable, then whatever sequence you take whose elements are either 2 or 3 should always belongs to S. Correct? So we're going to construct a sequence and we will show that the enumeration of that sequence never belongs to S. Okay? So if there is an enumeration, so let's say the first sequence is x and 1. Okay, so then the elements of the sequence can be written like this: x1 1, x2 1, and x3 1, and so on like this. Similarly, another elements from the set S can be written like this: x1 2, x2 2, x3 2, and so on. Similarly, xn 3 equals to x1 3, x2 3, x3 3, and so on like this. Okay, is it clear? Okay, and this will continue like this because we have assumed that the set S is countable. If the set is countable, then the sequence of the elements of the set S is just sequences, so we can count all the sequences. That means we can put labeling 1 2 3 like that. Correct? So that's why we can able to write all the sequences in the set S as xn1 xn2 and so on like this. Okay, so now we're going to construct a sequence in such a way that it will never belong to the set S. Okay, so you consider this sequence and you uh, take all the elements yn of I like this. So yn of I will be 2 uh, if uh, xi of I is 3, and take 3 if xi of I is 2. Okay, so what you are doing is you are taking the diagonal elements, so the elements x1 x2 x3, and then you are trying to form a sequence. Now how you are forming the sequence? So let's say if x1 of 1 is 1, I mean x1 of 1 is 2, then you're gonna take 3. If x1 of 1 is 3, then you're gonna take 2. Okay, similarly you do it for x2 to 2. If the element x2 of 2 is 2, you're gonna take 3. If it is 3, you're gonna take 2, because all the elements are either 2 or 3. Correct? So now by this way you can see that this sequence yn of I, or the elements of the sequence yn I, never belongs to this enumeration here. Now why is it true? Because the sequence, let's say if all the elements are matching, but at the ith diagonal element it will not match, because that's how we have constructed the sequence, right? Because if it match, like let's say all the elements of yn of I is matching from the above enumeration, but that ith diagonal element will not match, because if it was 3 we have replaced by 2, and if it was 2 we have replaced by 3. Correct? So let's say if the ith element is somewhere here, let's say if it was 2 we have replaced by 3 here, and if it was 3 we have replaced by 2. So that means if every element matches, but the diagonal ith element will never match. That's how we have considered the sequence. So from here we can say that the sequence yn from the set S will not have any enumeration, because it never belongs to the set S. So that means our assumption was incorrect, since we have assumed that S is uncountable. Sorry, S is countable. This is not true. So S must be uncountable. Is it clear for everyone? Do you guys have any doubts so far? Is it clear? You guys have to understand this, because using this Cantor diagonalization you can prove or you can solve a lot of questions. Is it clear? Because I'm going to spend 5 minutes here for you guys to go through it with me, and then we'll see if you guys can understand it or not. Yeah, I'm going to explain it once more. Yeah, there are also other ways to prove it. There are another way to prove it. I can show you. So it is using the power set. So you can show that the set of elements S is just 2 comma 3 to the power n, and it doesn't have a surjection. I mean, if you can prove that there is a surjection from this set S to the power set of n, then it will be a contradiction, because from a set of natural number to the set of power set of natural number cannot have a surjective map. Okay, so first let me go through the proof again. This is very standard proof. So see, it is given that the set of all sequences whose entries is either 2 or 3. Okay, so then the set can be written like this here. This is S. So S is collection of all sequences such that each element is either 2 or 3. Okay, so now if we say that S is countable, so we are assuming, let's say S is countable, then every element of S can be labeled using 1 2 3 like that, right? Because there will be an enumeration, right? So if there is an enumeration, then we can write S like this. So then S can be written like this: xn of 1, xn of 2, and so on, right? This is how you can write the elements of S, because I already said that, or we assumed that S is countable. Now if you see that each element of the set S is a sequence, right? Correct. Elements of the set S is a sequence. So that means xn of 1 is a sequence: x1 of 1, x2 of 1, x3 of 1. Correct. This is the sequence of first level, right? Similarly, xn2 is a sequence, xn3 is a sequence, and so on like this. So now we have written the enumeration of each sequences. So we have taken the first element from the set S as xn1, second element as xn2, and third element as xn3, and so on like this. So you write the enumeration of the first element, that is xn1, which is a sequence. So this will be x1 of 1, x2 of 1, and so on like this. Similarly, xn2 is also a sequence, which is the second element of the set S. This also can be written like this: x1 of 2, x2 of 2, x3 of 2, right? And similarly for xn of 3. So now what we have done is we have taken the diagonal sequence, okay, and constructed a new sequence. So if the first diagonal element is 2, you're gonna take 3. If it is 3, you're gonna take 2, because we have only 2 choices to take, because the elements are either 2 or 3, right? Similarly, the second element x2 of 2, if it is 3, you're gonna take 2. If it is 2, you're gonna take 3. So for example, if the first element is 2, this element is 3, and this element is again 2, then the first 3 elements of the sequence yn of I will look like 3 3 2. Okay, and then obviously it will go on like this. So if the first element is 2, let's say, second element is 3, third element is 2 again, then we're gonna take 2 as 3, 3 as 2, and again 2 as 3. So it will be like 3 3 2, and so on like this. So that means let me just so that means you have constructed a sequence where you have altered the elements of the diagonal element, where you have chosen xi of I as 3 when it is 2 and 2 when it is 3. So that means if this sequence cannot belongs to the above enumeration, because the sequence at least will differ in the ith diagonal element of that given sequence, right? Because if it, suppose let's say it is matching with xn of 3, then all the elements of yn of I can match with xn of 3 except x3 of 3, because if it was 2 we have taken 3, if it was 3 we have taken 2. Correct. So that means all elements can match at the best scenario, but the ith diagonal element cannot match. That's how we have constructed the sequence. So that means this enumeration or this sequence does not belong to the enumeration of S. So the assumptions we have taken in the beginning is not correct, which was S is countable, so S must be uncountable. So I hope this is clear. You can go through once again, and if you are still suffering to understand, I'm gonna refer to books. I think the instructor of this course has also referred to books. So the first book was uh, first course. So let me just check what uh, first course in real analysis probably. Yeah, a first course in uh, real analysis. This is by Protter and More. Okay, so this book you can follow, and there is another book. It's called Schemapa. And this is real analysis. This book also you can follow. Okay, so this proof must be given in either of these two books, so you can go and check after this class. Okay, so is there any doubt? Anyone? Is there any doubt? Yes. I'll be uploading these recordings in my YouTube channel, and then I'll be sharing the link with the NPTEL team, and they will be sharing with all of you guys. Okay, so don't worry about this video. You're gonna get this video in YouTube, but the main part is you all should understand this basic thing. I mean, this Cantor diagonalization. This is very important. Okay, so I'm gonna leave it right now for this question. So I'm gonna move on to the next question. So the next question is so let G subset of R be open and F subset of R be closed. Then so yeah, let me tick this one. It was uncountable. Then G minus F is so neither open nor closed nota. So nota means none of the following above. Okay, so let's come to the question. So I hope you guys have gone through the first week classes regarding matrix spaces, open set, closed sets. So then you might have known the definitions of open sets and closed set. Okay, so do anyone know the definition of an open set? So what is the definition of an open set in R? Let's say. So an open set means if you take any point on the set and then you choose a small interval. So the interval must be a subset of that set, right? So that means every point should be an interior point, correct? And what about closure? So a set is called closed if it is not open, or in other words, if it contains all of its limits point, right? So here G is open, and so so G is open, F is closed. They are asking about G minus F. Okay, so what is G minus F? So you are like subtracting the set F from G. Like now in set theory there is not such thing as subtracting a set, right? It's like eliminating the area of the set F from, or the elements F from G. So this is actually same as G intersection of F complement. Okay, so F complement means R minus F. Okay, so let's just better understand as F complement. So that means if this is a set, let's say R, this is G, then this is G complement. Okay, so now as I just stated earlier, that if a set is closed, its complement is open. Okay, so if F is closed, this will imply F complement is open. Okay, and we know that intersection of two open set is open, correct? So G intersection F complement must be open. Since intersection of two open sets is open, this will imply that G intersection F complement is also open. Okay, so now I am giving another question. So let me call the sub problem. So now can you tell me then what is F minus G? Is it closed, open, or neither open nor closed? So is the first one clear? Why it is open, everyone? G is open, F is closed, so G minus F is open. Is it clear for everyone, first of all? So yeah, are you guys listening to me? Have you guys understood why G minus F is G intersection F complement? Everyone? Is it clear? Tell me. If you don't tell me, then I will not understand, right? That you guys are getting it or not. Because I am just like speaking, I'm like, it's feeling like I'm doing the math, right? It's true that I'm doing the math, but you have to do it me as well, right? Then only you can understand. So how you guys get it? Why G intersection if complement is open? Okay, so I assume you guys have got it, that why it is open. Then what about F minus G? Anyone in the chat? If G minus F is open, what about F minus G? It is closed. Why it is closed? Yeah, this is true. Indeed, it is closed. But why? Why, what, and how? These are the three important questions of mathematics. Yeah, that is true. Yeah, that's correct. Because its complement, we have just showed that it is open, right? But you can go through the same process, that F minus G is same as F intersection G complement. Now this is closed. This is closed. So intersection is also closed. Correct. Okay. So let me uh, go to the next question, if there is no doubts. Uh, so the next question is gonna be from metric space. So I hope you all know the definition of a metric space, and if you don't, then probably let me first write the definition of a metric space, right? So yeah, can anyone tell me what is the definition of a metric and what is the definition of a metric space? Anyone? So a metric means it's a distance function, right? So let's say I have given you a set S. Let's say not S, let's say X. This is the standard notation. So a set is not that interesting, right? Because given a set, you cannot talk about its uh, open sets or closed sets or convergence of the elements on the set, right? You cannot talk about that, right? In general set theory. So to talk about these definitions like convergence, sets, open set, closed set, completeness, compactness, uh, you have to define a distance function. Okay, so in real number we have seen, or we have defined already some distance function. mm, yeah, this is the one condition of the definition of a metric space, that is the non-negativity. But there are also other criteria that has to be satisfied to become a metric. So first let me write what is a metric. So yeah, Bharat, this is true. Yeah. So given a set S, set X, uh, D, define D from X cross X to R positive. So this is close interval 0 infinity. Then D is called a metric if it satisfies the following conditions. Okay, so the first condition is, so see, given 2 point, let's say this is x and this is y, the distance should be always positive, right? The distance cannot be negative, because if you are defining a distance function, so in R we know the distance function is the modulus function, right? That you take 2 points x and y, let's say 5 and 3, the distance between the 5 and 3 is 2, right, in terms of the modulus distance, the L1 function. So distance means it has to be non-negative, so that means d of xy has to be greater or equals to 0 for each xy in x. Second property is, if the distance is 0, that means you have not gone anywhere, you are still finding the distance from a point to the same point. Because if you go from here to somewhere like here, you are drawing a straight line, and this does have a magnitude, right? So it will have some positive distance because you are traveling somewhere, right? And if you are not traveling, you are like sitting in a one positions, that means the travel distance by you is 0, since you are sitting on one positions. So if there is no travel distance, so that means you have never moved from that point, correct? So that means if d of x comma x is 0, this is will imply x to be 0. Okay, or in other words, if d of x comma y is 0, this will imply x comma y, x equals to y. Okay, the next property, anyone? No? This is better to write like this. So what is the third property? Anyone? So the third property is, if you go from x to y and then if you come back from y to x, the distance should not be changed, right? For example, if you're going from home to your college and then you're coming from college to your home by the same path, then you have traveled the same distance when you have gone to the college and then when you have come to your home, right? If you are following the same path, so that means the distance should be symmetric from the same path, right? So d of xy should be d of yx for each xy in x. And the third property is triangle property, right? So it says that if this is a point x, this is a point y, this is a point z, this is x, y and z, then the distance between x and z will be always less equals to the distance between xy plus yz, because this is how triangle inequality works, right? The triangle property works. So this is d of xz will be less equals to d of xy plus d of yz given x, y, z in x. Okay, so if these four properties are satisfied by this d on the set x, then d is called a metric. Okay, then okay, so already we have written that d is called a metric. So now if these conditions are satisfied on the set x, then the set x along with this distance is called a metric space. Okay, so then x comma d is called a metric space. Okay, is this definition clear to everyone? uh, is this definition clear to everyone? Yes, Bharat, this is true. This is called triangle property, right? Triangle inequality in terms of general metric. So yeah, okay, is it clear? This is last time I'm asking. If there is any doubt, you can ask me. Triangle inequality. So it says that if you go from like x to z, and the distance would be always less equals to distance between the two intermediate points. Okay, so this is like the generalization of the triangle inequality uh, in the modular form, right? For modulus distance, we know, right, x minus modulus of x minus y is always less equals to, I mean, modulus of x minus z is less equals to x minus y plus y minus z. I mean, modulus of. So that is how it is written. I mean, this is the, like, it is just generalization of the triangle inequality in the generalized metric space. Okay, so now uh, I'll be solving question from metric space. So this is question number 5. So define d from r cross r to r uh, by d of xy equals to modulus of x cube minus y cube. Okay, then which of the following is true? So the first option is d of x comma y equals to 0 uh, may not always imply x equals to y equals to 0. D is a metric on R. Third option is D is not a metric on R. And fourth option is not none of the following above. Okay, is this question clear to everyone? Yeah, is this question clear to everyone? Yes, it is modulus of x cube minus y cube. Is it not understandable? So this is modulus of x cube minus y cube. I think now it is clearly written. So now can you guys try and let me know how many properties you can verify from here. So I have written 4 properties of the metric space. Can you verify all of the properties? Okay, so since it's a modulus function, uh, so since it's a modulus function is always non-negative, right? So that means d of xy is greater equals to 0 for each xy in R, right? This is no doubt it is true. Second property is, so let's say dxy is 0. So this will imply modulus of xq minus yq is 0. Now if the modulus of a number is 0, that number has to be 0, right? So this is implying x cube minus y cube is also 0. Okay, so since x and y are real numbers, this will imply that x minus y into x square plus xy plus y square is 0. Okay, so you have two choices, either x equals to y, either xy is 0 or x square plus xy plus y square is 0. Now this one will imply correct. So this is same as so now you see that x and y both are real numbers. If y becomes non-zero, then anyone? If y becomes non-zero, x becomes complex number, right? Because inside exactly x has imaginary value, and that is not possible. So that means x has to be y. So this case is not possible, right? Because if y becomes non-zero, x will be an imaginary number, and that is not true because x and y are real numbers. So that means if d of xy is 0, x has to be equal to y. Third property is you see that d of xy equals to modulus of x cube minus y cube is same as minus of y cube minus x cube, and this is same as y cube minus x cube, because modulus of negative number is also positive, because inside modulus of a and modulus of minus of a is same. That's why these two are equal, and this is same as d of y comma x. So symmetric property also holds. Correct? What about the fourth one? Anyone? The triangle property? Okay, so d of xy, d of xz is x cube minus z cube, right? So this can be written as x cube minus y cube plus y cube minus z cube. And when by triangle inequality of modulus functions, we already know x cube minus y cube plus y cube minus z cube. And this is less equals to dxy plus dyz. So let xyz in R. Okay. So this verified the triangle inequality. Is it clear? Okay. If it is clear, then uh, I'll be going to the next question, which is question number 6. So let S1 equals to close 0 open 1 union 2, and S2 equals to union 2 in R with the usual metric. Okay. Then S1 and S2 are closed. Okay, so first let me tick the correct options. So D must be a metric on R. S1, S2 are closed. Second question is all points of S2 are limit points of S1. Third option is S2 is closed and 2 is an isolated point of S1. Okay, so two sets are given, S1 and S2. The first set is close 0 open 1 union 2 singleton 2. The second set is close interval 0 1 union singleton 2, and these two sets are taken in R with usual metric. So that means the metric space is here R comma D, and D is just the modulus function. Okay, so usual metric means always the modulus function, so that is D of x comma y is modulus of x minus y. Okay, so now can you guys guess like what are the properties of S1 and S2? And yeah, I mean, close definition already we have given that it should contain all the limit point. And what about the definition of isolated point? Do anyone know what is the definition of an isolated point? Anyone in the chat? S2 is closed. Yeah, but why? Why is it closed? So yeah, so first tell me what is the definition. Closed interval is closed. Yeah, this is true. Yeah, S2 is closed, indeed it is true. But what is the definition of a limit point and an isolated point? So first see that S2 is a union of two closed set, because singleton 2 is also closed and close interval 0 1 is also closed. So it's a union of two closed set, so it must be closed. But S1 is not closed, right? So here S2 is closed, but S1 is not closed. So why S1 is not closed? Anyone? Why S1 is not closed? So S1 was defined like this. So it's an union. Okay, so why S1 is not closed? Anyone? Yes, because it doesn't contain all of its limit point. So initially I said, right, the definition of a closed set is it has to contain all of its limit point. But here you see that one is a limit point. So what is meant by limit point? Limit point means, so there are a lot of definitions. So first definition is the it said that if you take an intersection, if you take a ball around that point, so it should have non-empty intersection other than that given point with the main set. Another definition is that a point is called a limit point if you can find a sequence from that set such that that sequence converges to that point. So here you see, if you take this sequence, this converges to 1 and xn belongs to S1 for all. So we have found a sequence from S1 that is converging to 1, but 1 does not belongs to S1. But 1 does not belongs to S1. So this is implying S1 is not closed. Okay. So we have got that S1 is closed, S1 is not closed, but S2 is closed. What about the isolated point? So a point is called an isolated point if it is not a limit point. Right? So isolated point means you can find an interval around that point such that if you take an intersection with the main set, it will have only that single point, not any other points. So here you see that this point 2 is completely separated from close interval 0 1 or close 0 open 1, because so if you take this ball, let's say 2 comma 1 by 2, then this ball intersection S1 minus 2 is empty. Correct. So first let me give the definition of an isolated point. So a point x in X is called an isolated point. So if there exists r greater than 0 such that bxr, so bxr is the ball around that point x, okay, intersection x minus singleton x is 5. Now what is bxr? So bxr is the open ball. So you take all point such that dxy is less than r. Okay, this is the open ball. Now here you can see that we have found a ball p of 2 comma half, let's say. Intersection s1 minus 2 is 5. It doesn't have any point, right? Because you choose a small interval, because see, this is close interval 0 1. So this is the point 0, this is the point 1, this is 0 and this is 2, and there are a lot of gaps. You can choose this interval. Let's say this is our bxr, right? So 2 is completely isolated from the set. Correct. So that's why 2 is an isolated point for both S1 and S2. Is it clear for everyone? The definition. So this should be an correct option. So all other options are not true. All points of S2 are limit points of S1. This is not correct because 1 is not an limit point of S1. S1 and S2 both are closed. This is also not true because S1 is closed. I mean S2 is closed, S1 is not. So is this isolated point argument clear to everyone? The definition of an isolated point and why in this case for both S1 and S2 2 is an isolated point. I hope it is clear, and if there are any doubts you can ask me in the next class always. So yeah, so let me go to the next question. Question number 7. Which of the following sets in R are perfect? So the first set is 2 comma 200 open interval. Second set is x in R such that 5 less equals to x less equals to 7.5 union 9. Close interval 1 comma 3 and node. Okay. So the question is given like this, that you have to tell me which of the following sets are perfect. So perfect set means a set which is closed and every point is a limit point of the set. I mean, if you take any point from the set, it has to be a limit point. So that means it does not contain any isolated point. A perfect set has to be closed and should not contain any isolated point. So a set S is called perfect if S is closed and it does not contains any isolated point. Okay, so you have to verify two things. One is the closeness, another is the isolated points. So now if you come to the question, you see the first set, which is open interval 2 comma 200, is not and closed set. So this is not a correct options. So this is not true. Second set is closed because it is closed interval 5 comma 7.5 union 9, which is union of two closed sets and closed. So it is a closed set, but it contains a isolated point. So as we have shown in the previous question, by the same argument, 2 was an isolated point. We can similarly show that 9 is a isolated point of this set. So that means this is also not true. But now come to this next option, that is closed interval 1 comma 3, which is a closed set plus every point it's a limit point, and also there is no isolated point. Correct? So that means option 3 is option 3 is correct. Is it clear to everyone why a closed interval is a perfect set? Okay, So we'll go to the next question. Question number 8. Let a equals to x comma y in R2 such that x square plus y square less equals to 4y. Then is now can anyone tell me what is a? So for this question I'm not gonna give any options because this is not that difficult, but to understand how you gonna proceed, so that's why this question is given. So yeah, can anyone tell me what the set A is, and in advance if you know the set is closed or open or anything, any like some properties you know? Anyone? Yeah. So this is a inequality given, right? That x square plus y square is less equals to 4y. So this will imply uh, that x square uh, plus y square minus 2 into 2y plus 4y square minus 4y square. I'm making some mistake here. This was 4y, right? So this is less equals to 0, and this is if and only if x square plus y minus 2 whole square less equals to 4. Correct? Because if you just expand the square, it will be y square minus 4y plus 4, and the 4 will get cancelled out on both sides, so you're gonna get to the previous inequality, which is x square plus y square minus 4y less equals to 0. So this is a circle. So A is a circle of radius 2 and center 0, 2, right? Yeah. So this is an advanced question. So now not at this stage we will be solving. This is an open or like this is an open set or closed set. But if you guys can guess it, I'll be very very happy. Like, is it a closed set or open set? Do you know anything? Because this is an application of continuous function. But yeah, I'm not gonna do it right now. But yeah, so one thing I can surely share that this is an closed set. This is not an open set. Yeah, it's a closed ball, right? This is a closed ball, right? So in fact it's a compact set. It's same as like a ball, right? In 2 dimension. So if you just draw the image, so this point will be just somewhere here. So yeah, this is gonna be 0, 2. This will be 0, 4, and this is of radius 2. Okay, this is the equation of the circle. So this is a ball, right? A ball is a closed ball. It's a compact, right? It's bounded and closed. So this all the definitions will be going through later in this course. I'm sorry. Okay, so now we'll be doing the last question for this class today. Is there any doubts for the question number 8? I hope no, right? Okay, so let A be an infinite set, then which of the following is true? A is always countable. A is always uncountable. Third question is there always exists an uncountable subset of A. There always exists an infinite subset of it. Okay, so let's say A is a given infinite set, any kind of infinite set. Then what can you say which is always true? Is it countable always? Is it always uncountable? Does there exist always an uncountable subset of it? Or does there always exist an infinite subset of it? Anyone? So I'm gonna give an idea. So first we'll be uh, doing it by showing some counter examples, because infinite set need not be countable always, or not necessarily be uncountable. So for example, you take A to be natural number set, then A is countable, right? Countably infinite. Similarly, you can take A to be R, then A is uncountable. So that means there are infinite sets which are not always countable or not always uncountable. So you can construct set which is infinite, can be countable or can be uncountable as well. So that means the first two options are incorrect. A is not necessarily always countable. Similarly, A is not necessarily uncountable. Now what about option third? So it says that there always exists an uncountable subset of A. This is not always true. So let's say A equals to the set of natural number or set of rational number. So since it's countable, every subset will be also countable. Correct? So there should not always exist an uncountable subset of A. Now what about question number 4? What about option number 4? So since the first three options are not correct, so obviously the fourth option should be correct. But why is it true that there always exists an infinite subset of A, given A is infinite? Okay, so I'll just give a hints why it's true. You guys can try to do it. So uh, it's a subset of R here, obviously. I mean, it's an infinite subset of R here we are talking about, or it can be any subset. So, actually, by well ordering theorem, you can just uh, make it well ordered, and then you can choose an element a1 in A, let's say. Okay, because A is an infinite set, there always exists an element a1, and then you can choose another element a2. Okay, from A minus a1, and then you can choose this collection a1 comma a2. Similarly, you can choose an element a3 from a minus a1 comma a2, because the set is infinite. Remember, there are infinitely many distinct elements. Correct? This is the definition of an infinite set. So in this way, you will be able to find a set S which contains elements like this, and it will go forever, right? So that means, given an infinite set, you will be always able to find a set S which contains infinite element, distinct element, which is of course a subset of A. So that means there always exists an infinite subset of a set A. Is it clear? So this is like a constructive example. Okay, because we don't know the elements of A, so we cannot explicitly show you the set. Correct? But you can construct an infinite subset of A. So first you choose an element, and that should always exist because A is an infinite set. It is non-empty. Then you choose the next element, which is from A minus A1, and then you go on like this. Okay, is it clear? So I hope it is clear, and if there is any doubt, you can ask me now or in the next class. And if there is not, then this is for today, and then we're gonna stop here. Is there any doubts, any questions, remarks, suggestions? Okay, so if there are not any questions, then I think I'm gonna stop today, and see you in the next class. Okay guys,